Thank you. I'm really excited to get to host this panel with two great speakers. We're going to start with Jessi. I was saying it right a moment ago. Cisewski and Casey King. Jessi's going to start off talking about outer space and I guess how we find planets from data, and then Casey's going to talk to us a bit about big data and human trafficking here on Earth. So I'll just turn it over to Jessi, and we're going to have two 20-minute talks, and then they're going to come up here and we'll ask them questions jointly.
Hello, thank you all for being here, and Kaylee for your great work in organizing. I was really excited to be asked to speak. So the theme is data on Earth, but we could think of it also as data on Earths. Right, so we're going to be looking for other planets, so that's what I will be discussing. This work is in collaboration that has grown over the past few years between Yale's Department of Astronomy, in particular led by Professor Deborah Fisher, and several PhD students and postdocs in that department. And then in my department, we have a couple PhD students and a postdoc, and then also several external collaborators, all of whom are astronomers. So what is the problem here? Well, ultimately, what we're trying to do is find exoplanets. And in particular, we want to find low-mass exoplanets, so Earth analogs we can even think of. And the problem is that when we're looking for low-mass exoplanets rather than Jupiter-like exoplanets, things like stellar activity, such as this large spot, maybe it's this large spot that we see here. This is a sunspot, right? So this is an image of our sun, and there is some activity that goes on the surface of stars, like our sun. And this spot here, it turns out, can cause problems. And the problem is that this can look like a planet when we're observing it from very far away. So what I'm going to focus on with this presentation is something quite simple. And what I'm going to try to demonstrate is that embedded in the data that we gather is a way to distinguish the signal from stellar activity like these spots here from the signal of a planet. So just to begin, so what is an exoplanet? It's a planet orbiting a star that's outside our solar system. Okay, so orbiting a star that's not our sun. And the search for exoplanets has become quite successful recently. So what we have here on the figure on the left is discovery year of an exoplanet. And then on the vertical axis, we have the cumulative number of detections. And then the colors are indicating the way or the manner in which the exoplanet was detected, at least first detected. And in red, we have what's called the radial velocity method. And that's what I'm going to be focusing on today, is using the radial velocity method to detect exoplanets. In green, we see that more recently it's been very successful. That's due to NASA's Kepler mission, which uses what's called the transit method for detecting exoplanets. So just monitoring the total light output from a star and looking for little dips, periodic dips, suggesting that a planet is transiting. So that's another great way of detecting exoplanets, but like I said, we'll be focusing on the radial velocity method, and I'll explain what that is. The figure on the right, we have the first publication date on the horizontal axis, and then on the vertical axis we have the minimum mass of the exoplanet that was detected. And we see that as the publication date increases, that we're finding more and more low mass exoplanets. But then there seems to be more recently this bottoming out, this we're kind of hitting a wall around 1.5 Earth masses. So that's the M sub E. So one Earth mass is the mass of the Earth, of course. And there's some issues with getting below this, this kind of threshold we have here, and in order to find Earth analogs, so these low mass exoplanets that we're seeking. Okay, so what is the radial velocity method? At its core, what we're looking for is a wobble in a star. So how do you detect a wobble in a star? Well, we have this very simple planetary system. The red ball is a star. The blue ball is a planet that's orbiting the star. And the X is the center of mass of the system. Due to the planet orbiting the star, the red ball is going to have some motion due to the gravitational pull from between the two objects. And if we are over here on the left, let's see if we can, over here on the left, and watching this star from Earth or just outside of Earth, looking at the star is going to have some forward and backward motion. Since this star, so really any object that's emitting light and is moving towards or away from us, something happens to the light output from that object. And in particular, if an object is moving towards us and emitting light, the light waves get kind of crunched together or blue shifted is what we'd call it. And when the object's moving away, the light gets stretched or red shifted. And we actually notice this with sound waves too. Like if you have an ambulance coming up behind you, it's very high pitched, high frequency, shorter sound waves. And then once the ambulance passes, it kind of drones off and it's kind of more low frequency. So sound waves and light waves have this similar property. And so what we are looking for then is a blue shifting and red shifting of the light from the star. And if we can detect this in some periodic pattern, that suggests that a planet is present, or at least some object orbiting the star is present. So what type of data would we gather? For the radial velocity method, we gather the stellar spectra. On the horizontal axis, we have wavelength, and the vertical axis is, you can think of it as the distribution of light coming from the star at these different wavelengths, or the intensity of light, or the number of photons hitting the CCD. And so if an object is orbiting the star that we're observing, if the star is moving away, this entire spectrum is going to move a little bit to the higher wavelengths, right? It's going to shift a little bit to the right, and then when it's moving towards us, it'll shift towards the bluer wavelengths, so a little bit to the left. That sounds like it should be easy to find, but these shifts would basically be indetectable if I were to show you the shifted curve, unless it was a very massive exoplanet. So what is typically done then is that spectrum is turned into a single number, and that number is the estimated radial velocity of the star at the particular time that the spectrum was gathered, the data were collected. And so if you do that across time, so you get a time series of these stellar spectra, and you turn each into one number, you can plot what's called the RV curve, the radial velocity curve for the star. And so here I'm showing one from 1995. It's 51 Pegasi, and with these data, they discovered an exoplanet, and that exoplanet is about 150 Earth masses. And this negative to positive to negative pattern that we see here, so think of phase for now just as time. So across time, the star is moving towards and away and towards us. And the SemiAmplitude here is about 50 meters per second. Okay, so it's from detecting this shape in the radial velocity curve that suggested that an object is orbiting, and due to various theorems and laws and things, we can actually estimate the mass of the planet from this. Okay, so this was from 1995. And then if we look at a more recent data set, this is from 2011, where they also detected an exoplanet that is a minimum mass of 3.6 Earth masses. And suddenly the pattern's not so clear, right? So it turns out that the SemiAmplitude is about 0.8 meters per second. We see that there's a lot of scatter. There's uncertainty in the measurements, but ultimately they were able to discern this curve that suggested an exoplanet is present. Okay, so between 1995 and 2011, the instrument that was used to gather these data dramatically improved, which was why there's even any hope at detecting an exoplanet of this mass. Okay, so again, about 1 meter per second is the semi-amplitude. So with that in mind, what we want to find are Earth analogs. And so looking for an Earth-like exoplanet orbiting a sun-like star, we have to be able to detect a semi-amplitude of 9 centimeters per second. Okay, so that's, so again, this is about 1 meter, and what we're looking for is a signal that's about 9 centimeters per second. So the instruments that are being built, the spectrographs, have been improving, and at the end I'm going to mention one of the newest spectrographs that was developed by an astronomer here that gives us some hope that we might actually be able, in terms of the instrument, be able to get to this level of precision in order to detect Earth analogs. But it turns out that that's not the entire problem. So the instrument is one part of it, making sure that we have the resolution needed in order to detect such a tiny shift. But then it turns out once we get down to that level of precision in the data, there's something else that comes up. And I already mentioned this near the beginning, but the problem is with stellar activity. So stars are not solids. They're actually a plasma. Lots of things are going on, magnetic activity, a lot of motion. And so there, all these different effects happening on the star can cause distortions in the data, which isn't necessarily a problem until those distortions end up looking periodic. And when they start looking periodic in a particular way, that's when they start to look like exoplanets. And so it turns out that if there is a spot present on a star, that spot, it can move, it can shrink, it can grow, it's not going to live forever, it might have a lifespan of days to weeks, but it will rotate with the star, and due to certain other properties, in particular the fact that when a star is rotating, half the light from the star is coming towards us, the other half is going away. So half of it gets blue shifted, the other half red shifted. If you start considering spots, like these dark regions here, and that spot is rotating from a blue shifted region to a red shifted region, in the data, that starts to look like a Doppler shift. Okay, so we need to be able to discriminate the effect of stellar activity from the effect of a real Doppler shift in order to detect exoplanets successfully. The risk is if we don't do that, we will come up with false detections, and then the field can lose credibility, people stop trusting when a real detection happens, and so forth. So we don't want to have false detections. That's not good. So the question then is, can we disentangle stellar activity and Doppler shifts by actually looking at the spectra? Right, so previously we would take the whole spectrum, turn it into one number, and now our question is, can we go back out to the spectrum and get more information than that one number summary? And so what we're going to look at next is a time series of simulated spectra where I'm going to demonstrate that the effect due to a single spot can be discriminated from the effect due to a single planet. It's a very simple idea, but we first wanted to demonstrate that that information content was even in the spectrum, or in the spectra. So what I'm going to use is our simulated spectra from the spot, oscillation, and planet code. This is an example of a simulated spectrum. It's actually using real spectra from the sun and then putting a real spot spectrum into the data. So what we're going to do then is add a spot that has a coverage area of 0.1%, a spot with a coverage area of 1%, and then 5%. So these are increasing sizes of spots, and that's going to be 3 separate data sets. And then we're going to consider 3 data sets with a planet. One has a 1 meter per second planet, a 10 meter per second planet, and a 50 meter per second planet. So that this is increasing the strength of the signal coming from a planet. And so each of these 6 data sets have a time series of 25 spectra. And we're going to look at what happens to the spectra with these different effects applied to it. All right, so Many of you, I'm sure, are familiar with principal component analyses, right? Most introductory stat courses will cover this, but not everyone has taken stat courses. So I'm just going to mention that what we do, just to investigate details in the spectra, is we take each spectrum. Let's say there are 100,000 measurements on one spectrum. So instead of thinking of it as a spectrum, think of it as a point in a 100,000 dimensional space, right? Really easy to imagine. And then we're going to look for the directions of the most variability among those wavelengths. So here I just have a three-dimensional projection. So each dimension is a different wavelength, and then each point is that representing that part of the spectrum. And so the first principal component finds where most of the variability is. And so that's that one arrow with the PC1 on it. And then PC2 finds the next direction of variability orthogonal to that first one and defines that direction, and then it continues on in that manner. So the first principal component captures the most variability, second principal component has the second most variability, and then so forth. So we're going to then take those directions and color the spectrum according, you can think of it almost as weights. So the first principal component is telling us how much of each wavelength is contributing to that direction, and they can contribute in sort of an opposite way, positive or negative, or close to zero where it's not really contributing much. And so it says facula there. We're just going to ignore the facula for now and only look at the spot and the planet. So here we have these three figures, and they're each cutting out a portion of the spectrum, and the redder regions have a positive weight, and the blue regions are negative weights. And if you compare the spot versus the planet, you'll see that the blue versus the red is different between them. The planet is actually doing just what we'd expect. We'd expect half the line to look blue, the other half to look red. That's what would happen if you just imagine taking one of these, one part of the spectrum and shifting it. The variability is going to be opposite on each side. But then with the spot, it's doing something different. The core of some of the lines, let's see. The 17.5, the core of the line is red, and then when you get towards the top of the line, it turns blue. So it's doing something different from what the planet's doing. So that's a good sign. It's saying that somehow the information due to the spot is behaving differently from that of a planet. And then what we started to look at is, okay, well, the simulated data is essentially perfect data. There was no noise added. It was high resolution, so we had a lot of information. What if we start playing with the level of noise and playing with the resolution? And then we wanted to count how many principal components we could count as we change the amount of noise and the resolution. And so I won't go into, just due to time, I'm not going to go into many of the details here, but if you look at the left column and the right column, this is colored according to how many principal components were discernible from noise. And again, we see that the planet versus the spot looks different. And in fact, the variability due to the spot is somehow distributing into the components differently from the planet. All right, so that gave us hope that the patterns look different, and so that we can be developing methods now to better discriminate stellar activity from Doppler shifts. And I had mentioned near the beginning that there's a new spectrograph that has been developed. Professor Deborah Fisher is in the white lab coat, sitting down, and then some of us statisticians are just in awe of this instrument that she built with her team. But it's already providing very clean, high resolution, stable data. And just to illustrate, this figure on the right, on the left is the 51 Pegasi dataset from 1995 that I showed earlier, and you see the scatter that's present there. On the right, this is kind of the first check of Express, and already we can see that the data, this is with the noise too, that it's significantly better from what we've had previously. And so the hope is with the statistical methods we're developing and some other aspects of projects we're working on that we'll be able to detect Earth analogs soon. Okay, so with that, I'll conclude and just say that the radial velocity method has been quite successful. There are some problems due to stellar activity. There's a bunch of us, especially here at Yale, working on it, and it's very exciting, lots of interesting statistical challenges, and we're hopefully going to have some really great data soon. So thank you.